In this video, we're going to look at Stokes' theorem. But first, let's recall previously we had Green's theorem. And we said that that relates to the line integral. Say around the boundary of an area. To the double integral over the area itself. So, for example, if you have some kind of area here in the XY plane, and you have some boundary, say the boundary is C, and then you have some domain D inside. So again, you have like a closed curve, and then you have some area inside. This can be done with Green. You will have like, say, P dx plus Q dy is equal to dq dx minus dp dy dA. In other words, the integral around this boundary is equal to the double integral over this area inside the boundary. And then the integrand for this, if this is P dx Q dy, this is Q dx minus P dy, the partial derivatives of each of those. Now, Stokes' theorem looks very similar to Green's theorem, except it's in 3 dimensions. And so, like, for example, maybe you have something like this here, and maybe you have some boundary like out here in 3 dimensions. Some boundary C. And then you have a surface inside. Again, let's maybe call this S, some surface in here. So Stokes' theorem relates the line integral around the boundary of the surface say call it S, to the surface integral over S. So you might have, let's say, maybe a line integral of this form here. That's going to be equal to the surface integral. And what you have here is the curl of F. You could write it like this, or like this, dot ds, like this. And of course, the curl of F, this can also be written in this way with that operator. Now again, it could be like a surface like this, or you could even think of it a case where, let's say, you have maybe, say, a paraboloid or something like that out here. And you can sort of think of this lower boundary here around the bottom of the paraboloid as being the boundary of the surface. So you can almost think of it like being Green's theorem, where that area in between is kind of pushed upward. Like I said over here, for Green's, you had like this area here, but you can imagine it pushing upward. And instead of being in 2 dimensions, it's in 3 dimensions. So you have this surface here. And now we're also going to have to talk about positive and negative orientation. If the normal or perpendicular to the surface is, let's say it's pointing this way, or over here, it's pointing, let's say, upward. Let's say this is pointing maybe upward from the surface here. Again, these are the normals or perpendiculars to the surface. And we'll define positive orientation. And let me maybe keep this picture in mind here. Positive orientation on the boundary curve C would be defined this way. If you walk along C, with your head pointed in the direction of the normal, then the surface will always be to your left. That's considered positive orientation. So once again, you can imagine, let's say, if you're standing, walking around this boundary here in the direction of the arrows, of course, is what it means. So let's say you're standing up here, walking along here. Notice the boundary is to your left. Your head's in the same direction as N. then the boundary is going to be to your left. That would be positive. Same thing over here. If you're walking along here, the way N is pointed, the boundary is going to be I should say the surface. Sorry, the surface is always to your left. The surface will always be to your left. Now, if somebody had defined, like say in this case here, if they had defined the normal downward, then if you were walking with your head pointed in that direction, say downward, you'll notice if you're walking along this curve, the surface would be to your right. So that would be negative orientation. Because don't forget, on any particular surface, you can define a positive normal or a negative normal. So in the problem, they would have to tell you which they've defined as positive. So in this case, if the positive is pointing this way, then this would end up being positive orientation. If they had defined the normal going inward, then notice if you're walking in with your head in that direction, it'd be like on the bottom of this, it would be negative orientation. And of course, if it's negative orientation, you would just change the integral to a negative when you do it. But in the problem, they would have to either tell you what direction that these are pointing, or sometimes they'll just say positive orientation, and then you can just automatically know that you have positive orientation. One other thing I should mention, just for notation wise, the problems are kind of worked out always the same way, but so this is Stokes' theorem. Also, sometimes you can write this a double integral as curl of f dot n ds without the vector. So let's take a look at some problems. So let's take a look at this problem here. We have this line integral where C is the boundary. I should have had the word boundary in here. Is the boundary of the plane x plus 2y plus 2z is equal to 4 in the first octant, positively oriented. And we're going to evaluate this using Stokes' theorem. So once again, let's keep the equation in front of us for Stokes. So again, it's going to be the FDR is equal to the double integral over the surface. And we'll use this form, curl f dot n ds, like this. And so let's take a look at this. So starting out at the beginning here, notice that it's this plane here. And so it says in the first octant. So let's draw that. Of course, you remember how to draw the plane in the, say, the first octant. You can set two of these variables at a time equal to 0. So like, for example, if you set y and z equal to 0, that'll give you x equal 4. So 4, 0, 0. And if you set, say, x and z equal to 0, that'll give you 2y equals 4. So y is going to be equal to 2. So that'd be 0, 2, 0. And then set x and y equal to 0. And that'll give you 2z equal to 4. So it's going to give you z equal to 2. Just something like this. And then we can draw a little picture here just to give us an idea of what's going on. And we're going to have like a 4 here, 2 here, 2 here, like that. And we're told it's positively oriented, so we really don't even have to think about that part too much. So the normal, so we can think, okay, the boundary C looks like this. And then there's a normal coming outward out of that. I won't even draw that. But a couple of things to keep in mind. If you recall from what we did before, if you want the normal vector, you can solve your surface. So we want the normal to this surface. So go back to the surface up here. X plus 2y plus 2z is 4. So remember, solve this for z. And that'll give you like a function. A lot of times they'll write this as a function g, x, y, just to kind of tell you it's going to end up with a function of x and y. So in any case, solve this for z. So we'll bring x to the right, and we'll bring y to the right, and then divide by 2. So let me just leave those empty for just a second. And when we bring those to the right, we're going to get negatives here. And notice that when we bring those to the right and divide by 2, we're going to have x over 2. And divide by 2, we're going to end up with y will just be 1 in front of it. And divide by 2, and we'll have 2 over there. And again, remember when you have something in this form, you have your surface. In this form, you can find your normal by doing negative dg dx, negative dg dy, and 1. So remember that's one way you can find a normal vector if you have, your surface as a function of x and y. We have like z equal to a function of x and y. Then you take the dg dx, dg dy, and 1. And so let's do that in this case and put a negative in front. So if we take the derivative here with respect to x of this, that'll give us negative a half, but that'll be negated by this negative, so that'll be 1/2. And over here, take the derivative with respect to y. That'll be dg dy. That'll be -1, but that'll be minus a minus, give us a positive 1. And then finally, the last component on this is always 1. That's going to be our normal. And you can kind of think of that. You can kind of think, oh, yeah, if all those components are positive, that sort of makes sense. That looks like that's going to be kind of pointing upward away from this, up and away from this surface, because those are all positive. So that's our normal. And then we're going to need the curl, as we have in our equation here. And remember, the curl is defined this way. And remember, that's I, J, K, or you may have a different way of memorizing the formula. I usually just put it into the determinant. And then we want the curl of this up here. So that'll be y squared, x squared. And I didn't leave myself much room here. this will be z squared minus x. And then, of course, do the determinant. Remember, just go across the top here. And this will be I. And then this will be, remember, will be this times this. Now, in this case, you're taking the derivative. So it's saying take the derivative with respect to y of this over here. And that's going to be 0. Then minus the derivative of this here with respect to z. Well, that's going to be 0. Then we go to j. Remember, the j is always negative. And then we want the derivative of this one with respect to x. That would just give us a -1 minus the derivative of this dz with respect y squared, take to that with respect to z, which is just going to be 0. Then finally, this one, we're finally going to get some more numbers. So there'll be the derivative of this with respect to x. That'll be 2x. And derivative of this with respect to y, that'll be 2y. And a lot of times I like to write this with the angle brackets. So this was the curl. So let me actually just rewrite it like this. And there'll be 0. And this will be negative of a -1. That'll be 1. And this is going to be 2x minus 2y, like that. So we have most of the parts now. We have our vector n. And actually, I should have written this as a little vector notation here. We have our vector n. We have our curl. And now we can put everything into our integral. So once again, we'll just keep in mind what we're doing here. We're doing this line integral dot dr is equal to the curl. Again, remember that's this dot n ds. But then we found this over here. We found the curl, which was 0, 1, 2x minus y. And we're going to dot it with our n we had up here, 1/2, 1, 1. The s. And by the way, this should be an s right here. And we work this out. This is going to be 1. Remember, this is do the dot product, that's 0. And then that would be 1 plus 2x minus 2y ds, like this. And then now we're going to need the domain of integration. And so, like, remember up here, so this was our surface. Then our domain for our integration could be down here. Remember, it's always going to be like in the XY plane where the surface is projected down the XY plane. So it'll be in the XY plane, and it'll be from 4 in the X to 2 in the Y. Let me redraw that in the XY plane over here. So it's 2 over here, 4 over here. Draw that like that. That's going to actually end up being our domain when we change, integrate this over this area. And of course, we'll need the equation of that line. And so what's this going to be? A slope. This is going to be 2 down and 4 over. So rise over run. And it's negative. It's going downward. So the slope will be negative 2 over 4, or a half. Again, we're going down 2 and over 4, 2 over 4, 1/2. Then our y-intercept is 2, like that. So now we can put this together with now that we have our domain, we can do, this will become like dA over here. This will be 1 plus 2x minus 2y dA. And then from y equals 0 to y equal minus 1/2 x plus 2. Then on the x bounds would go from 0 to 4, like that. And now the rest is just the mechanics of doing that double integral. So I'll just leave that. I'll stop right there because that's probably something you're able to do pretty easily now. But again, let's just review what we did. We wanted to evaluate this using Stoke's theorem. We did the curl. Again, we identified when you do the curl, it's going to be dx, dy, dz, and these components here. Do the curl, we got this. We found the normal to the surface by doing the derivative of our surface, like this. Put everything into Stokes. Calculated this way. Then we need to find the domain of integration. Again, that's always kind of like what's projected on the XY plane. We did that, and then this. So let's take a look at this problem here. We're asked to evaluate this line integral, FDR, where our vector field is given this way. And C is the curve, which is formed by the intersection of the surface and the cylinder, x squared plus y squared. I meant to say 9. X squared plus y squared is equal to 9. And with positive orientation. So once again, keep in mind Stokes' theorem. I won't write it down again, but I'll write it down at the end. But remember, we're going to end up needing the curl. And also, again, we have like this intersection. We really don't need to know exactly what this surface looks like, but remember, this here is a cylinder of radius 3. So it would look probably something, like this. Radius 3. And then there's a surface somewhere in here. And this is the boundary. The C is the boundary of that surface. And so we're going to use Stokes to evaluate this. Now, in a few minutes, we're going to need to see the domain because we're going to be integrating over this surface in here, like I said, somewhere in here. And the domain will be in the XY plane. That's going to end up being our domain of integration. You'll see that in a minute, but I just want to get a head start on that. So that's going to be in the XY plane. That we're going to integrate. This would be like our domain of integration when we get to that point. It looks like I realize that it's not clear now why I'm doing this, but we'll see in a few minutes. In any case, we're going to need to do the curl of this. And again, let me actually just write this out a little bit more nicely, this vector field F. Let me write it here just so we can have it in a little bit cleaner form. Like this. So we're going to need the curl of that. So the curl, of course, is going to be this cross product. So it'll be I, J, K, dx, ddx, ddy, ddz. That's going to be minus 1/3 y cubed, 8 minus xy squared, xy, like that. And so let's do the cross product. Remember, we have I. So we cover up that row and that column. So we're going to have the derivative of this with respect to y. So it's going to be x. Then the derivative of this with respect to z, that's going to be 0. Then over here, derivative of this with respect to x, which is going to be y. And then the derivative of this with respect to z, which is going to be 0. Then finally, we're going to have the derivative of this with respect to x, which is going to be negative y squared. Then the derivative of this with respect to y. And of course, that would be a minus of a minus. That's going to be y squared, a minus y squared. So that's going to end up being 0. And so we're going to end up with, let me write this as x negative y, and that's just going to be 0, like that. So now, remember, we're going to need our normal to the surface. So our surface is given this way. So that reminds us again, so we have z as a function, and you can think of that as a function of x and y. You don't need to put that in, but it's helpful to think of it that way. So z is this function of x and y squared minus x squared. And then we're going to need to find the normal. And remember the normal, whenever you have the surface in this form, the normal vector to the surface is going to be negative dg dx, negative dg dy, and 1. And now we just about have everything we need. And let me just to remind us, write down Stoke's theorem, which is we originally were asked to do this line integral, and instead we're doing this surface integral, curl of f dot n ds, and we found the curl over here, which was x minus y, 0, dotted with our normal. And I wrote this normal pair, I forgot to actually calculate it out. So this is going to be dg dx with a negative. So that'll end up being a positive 2x. We'll take the dg dx, it'll be a positive 2x. Then take dg dy, which will be a negative 2y and 1. That's our normal. 2x minus 2y and 1 ds. Multiply this out. That'll give us 2x squared plus 2y squared plus 0 ds. So now we have to integrate this. Remember, integrate over our domain. Remember, we have this surface here, the projection in the xy plane. Our domain was a circle radius 3. And so let me and I'm just going to put this circle radius of 3, because we're going to end. Let me factor out the 2, x squared plus y squared dA. And of course, since it's a circle, we'll just change the polar to make it easier. So there's going to be 2. And remember, we changed the polar. It's going to be r squared. X squared plus y squared is r squared. Then when we have to put in the Jacobian, the r, always remember, put that in when you ever change the polar. And then our bounds are going to be from r equals 0 to r equals 3, because we have a circle radius 3, theta 0, theta to pi to 2 pi. And if we multiply this out, that would be r cubed. Then we integrate that. That'll be r to the 4th over 4. R equals 0, r equals 3, d theta. And we could cancel, we have a 2, we could cancel that. That would give us like a half. And then put this in. And so I made that half. 3 to the 4th, that'd be 3. 3, I think that's 81. And integrate again. and put that in. So it's going to be 81 times 2 pi. The 2's will cancel. So I think that would just be 81 pi. Let's take a look at this problem here. Evaluate this line integral where c is the circle x squared plus y squared equals z squared. It's z equals 5. And we're given our vector field. I got this problem from a textbook. And so let's see what we have here. So we have a circle of radius 4, as you can see, and it's out and up off the plane. Looks like it's out here. Curve C like this. And so we're asked to do this line integral, but we'll use Stokes, and so instead we'll use the surface inside the boundary of that curve. And of course, that's going to be this surface here at z equal 5. So let me just put a 5 in here. So we're up at z equal 5. Now, one thing to keep in mind when you have something like this, if you have, like, say, just a circle, or this could be like the end of a cylinder, something like that, the normal is pretty simple. Remember, the normal is perpendicular to that surface. So the normal, let me maybe do it over here so you can see it better. The normal will be up this way. So the normal vector is going to be, and you can see that's going to be perpendicular to that area inside the circle. And that's just going to be what? 0 on the x, 0 on the y, and 1 on the z. That'll give us that normal to this area here. And so we have our normal vector. Next thing we're going to need is the curl. And of course, put your vector field down here. Like this. And then do the curl. Again, that'll be derivative of this with respect to y, which is going to be x e to the xy. Then derivative this with respect to z, which is going to be minus 2xz, excuse me, 2x. Then minus j, derivative this with respect to y, excuse me, with respect to x, which is y, exy. Derivative this with respect to z, which is going to be, and then there'll be a minus, so it'll be minus y. And then plus k. Derivative this with respect to x, that'll give us 2z. Derivative this with respect to y, that'll just be z. Like this. So just double check my derivatives. This derivative, this with respect to y is x e to xy. With respect to z, that'll be minus 2x. Over here, derivative with respect to x is y e to xy. Derivative with respect to z is minus y. And then this is going to be 2z minus z. So then, so we can do Stokes. So that looks pretty messy. Remember our FDR going to be the double integral. And again, it's going to be this here. That's going to be the curl x e x y minus 2x. And this will be a negative, and then negative, that's going to end up being negative y e x y plus y. And this is just going to be 2z minus z, so it'll just be z. And then dotted with the normal 0, 0, 1. The S. And notice now, this will be 0. We multiply that. And then do the dot product here. That'll be 0 plus z. So we just end up with z ds like that. So now remember, whenever we end up, like, say, with a z in here, we're always going to replace that with our value, its value in the on the surface. Now, in this case, z was equal to 5. So we can just replace z with 5. And then also think of what our domain of integration is going to be. That's going to be like how this projects onto the xy plane. And so that's going to be a circle, isn't it? That's going to be a circle of radius 4, because this was x squared plus y squared is equal to 4 squared dA. And of course, when we're doing a circle, well, a couple things to remember here. We'll do a circle. You could change the polar coordinates and do that. But always remember, if you ever get down to the point where you have a double integral with just dA right here and nothing, no variables at all in here, that double integral, remember, is just going to be the area of your domain. Now, you can only do this when you have just dA left. If you had any variables here at all, you couldn't do that. But if you get down to this point, you have double integral, that's just the area of your domain. And now in this case, it's a circle of radius 4. So our area is pi r squared. And that'll be 80 pi. That. so again, just a couple things to remember here. As I mentioned before, you have the circle here, and you kind of wonder, well, how do I get a normal vector that to that surface inside here? In fact, because before we said the normal vector is found when you take the derivatives of z equal this function, but you don't have anything like this here. But so just think of your geometry that you have a flat surface here, so a normal is going to be pointed this way. And I probably should have mentioned the problem here. I probably should have said beginning here, but it was positively oriented, so it would be up that way. So the normal is just like that. Then the other thing to remember, again, if you forgot, it'd be okay. You could do the polar coordinates and do the double integral, but take it, more time. Instead, just always remember, if you get to this point and now if you didn't know the area here, then, of your domain, then you would have to integrate anyway. But if you know the area of your domain, you can just put it in. Let's take a look at this problem. I also got this from a textbook. Use Stokes' theorem to evaluate this line integral where this is our vector field, x, y, x squared plus y squared, and C is the boundary of the part of the paraboloid 1 minus x squared minus y squared in the first octant. So let's take a look at that. Once again, it is sometimes helpful to just draw our paraboloid. And it's going to go something down like this. And we can say, let me say it's positively oriented. We'll assume it's positively oriented. And so our boundary C is going to kind of go around the bottom like that. And we have our normal vector out here. And also, again, a little bit later when we think of the domain, because we're going to end up with a surface integral, we're going to need our domain. And so this intersects the xy plane where z equals 0, of course. So if we set z equals 0, we'll get x squared plus y squared is 1 squared, or 1. That's going to end up being our domain later when we do the double integral. Like this. And so let's take a look at this. So as usual, we're going to need the curl. ddx, ddy, ddz. And our vector field is x, y, x squared plus y squared. And let's do our cross product. Again, it's this times this. This is the derivative of that. So derivative with respect to y is going to be 2y minus derivative to that with respect to z is 0 minus j. Derivative to this with respect to x is going to be 2x. Derivative to this with respect to z is going to be 0. And finally, we do this one here. We'll have this one over here. This will be 0, 0 minus 0. We want 0 minus 0 like that. And so our curl is going to be, looks like 2y, negative 2x, and 0. Then we can use find our normal vector here. Again, our function is a function of x and y. And then our normal vector, remember it's going to be dg dx, negative dg dy, and 1. And so in this case, this will be negative 2x, but will be the negative of that. Derivative to this with respect to y, negative of a negative 2y, and 1, which is going to be 2x, 2y, and 1. That's going to be our normal vector. And then let's put in our, so let's use Stoke's theorem now. Just remind us what Stokes is. We could say curl of f would do the cross product dot n ds, and we'll put all of our stuff in. Our curl was 2y minus 2x and 0, dotted with our normal over here, which is 2x, 2y, and 1 ds. That would be 2xy minus 2xy plus 0 dA. That's all just going to be 0. And excuse me, this would be ds here still until we actually put the domain as dA, but we're going to end up getting 0 like this.